So if you watch at the top here, you'll see some products come flying in from outer space. Okay, add in some more of the red and yellow things, which instantaneously does what? Increases the concentration of the products. Okay, so we're gonna, why am I going backwards? Wake up, Warren. Increases the concentration of the products. So the products goes up on the graph. Right? Because the volume will have increased, that means the reactant concentration must go down. Now, if the product concentration has gone up, what's going to happen to the reverse reaction rate? If the product concentration has gone up, there's a higher concentration of products, what happens to the reverse reaction rate? Increases. So that means the bottom reaction, the backwards reaction arrow gets bigger. What does that do to the amount of reactants? Concentration of reactants. Increases it. What does that do to the forward reaction rate? Increases it. So the amount of products reduces, the amounts of products reduce because the reverse reaction rate is increased. That makes the amount of reactants increase because more reactants are being formed, which increases the rate of the forward reaction. So now you get a new equilibrium established, and it has shifted, you can see, to the left. Equilibrium has shifted to the left. The formation of reactants has been favored. So then there I've got it in words. The new equilibrium setup, which has been shifted to the left. Now if you look at this little thing down here, watch. This is a nice little way to remember of how this works. You increased something on the left, and the equilibrium shifted to the left. So you increased something on the right, and the equilibrium shifted to the left. All right. So I think that's a nice little way of learning it. As you add more product, point of concentration increases, therefore reactant intensity decreases, reverse reaction rate increases, product concentration decreases, reactant concentration increases, forward reaction rate increases. New equilibrium is established with a lower ratio of products to reactants, being shifted to the left. All right. You've got to be able to talk your way right through that whole thing. More than that, you need to be able to predict which way an equilibrium is going to shift if we make a change. Probably not 6, but 3 or 4. All right. So product was added, the equilibrium shifted to the left. So predicting the effect. The guy who first documented this was a guy called Le Chatelier. My French pronunciation is not very good. And that's his principle, which you will, I guarantee you're going to be asked. Connie, you're being rude. You're disturbing him and me. So the Chatelier's principle basically explains what's going on there. It says if the condition of the equilibrium system are changed, then the process will take place which tends to oppose the change that's been imposed. It's kind of like somebody says to you, sit down, and you say, no, I don't want to sit down, I want to stand up. And you say, stand up. No, I want to sit down. The reactions are exactly the same. You increase the products, it shifts to decrease the product. You increase reactants, it shifts to decrease the reactants. If a change is opposed, is instituted which opposes what you do to it. You could call it the student effect if you wanted to. So Le Chatelier's principle, we're gonna ask it to you at some point. You've got to learn it, word perfect like a definition. And then you're going to have to apply it. So you should be able to say over here what all of these changes are going to do. I've done the first one for you. If you increase the reactant concentration, what happens? The equilibrium shifts in the direction of using up the reactant. So it shifts to the right-hand side. Do the others, please. What's going to happen if you decrease the reactant concentration? Which way is it going to shift? Fix it, change it. You should be typing, Mr. Pillay. What do you think is going to happen if you increase the pressure of the gases in a reaction? if you just apply Le Chatelier's principle. If you increase the pressure in a reaction which has got gases in it, it's going to shift to decrease the pressure. Now, if it can decrease the pressure, it will. Right? There are some reactions where there's more moles of gas on one side. So if it shifts to the side with the least amount of gas, it will decrease the pressure. If there's no gases in the reaction, it won't affect it. But if there are gases in the reaction, and you increase the pressure on it, it'll shift to the side where there's less gases. That's if you increase the pressure. If you decrease the pressure, it'll do the opposite. Increase temperature. What's it going to do? You get exothermic and endothermic reactions. If you increase the temperature, it's going to shift to the endothermic. It's going to shift in the endothermic direction. So it's going to use up that extra heat, and the endothermic reaction will be favored. If you decrease the temperature, the opposite will happen. What's going to happen if you add a catalyst? What does the catalyst do? Won't be a shift. It decreases the activation energy, but that applies to both reactions equally. So that's a change, and that's a shift. So we'll have to tell you. Unless it's something that you should know, like, for example, all acid-base reactions are exothermic. All combustion reactions are exothermic. But combustion reactions are generally not reversible. The acid and base reactions are. But we would tell you if it's endothermic or exothermic. You know, we'll give you delta H. You know, delta H is less than 0. So by using those criteria, you should be able to predict which way the reaction is going to shift. And we will ask you those. You're definitely going to get examples. And the way we'll ask it is probably not in general theory like this. We'll just give you a specific example. We'll give you a reaction equation. They'll say, right, the amount of this stuff is increased. And we normally, what they'll do is they'll give you a reaction. You'll see some examples in a minute. We'll give you a reaction. We'll tell you the color of the reactants and the color of products. And we'll say, we're going to increase this. What color is the reaction going to go? Or we'll say to you, if we want the reaction to go blue, what change must we make? And you will have to use these things to predict it. All right, can I move on? Yep. So let's look at a couple of examples. So this is a reaction that's fairly well known. It's hydrogen and iodine reacting to form hydrogen iodide gas. Delta H is quoted here, -13. So that's telling you it's exothermic. All right. Lesson doesn't end till 15:15, doesn't it? Say that again. Good question. So if it's written on the right, then it's the forward reaction. Yeah, this lesson only ends at 10:15. I don't know why people are walking around. So, you know, if we write it like that, then we're saying the forward reaction is exothermic. Now, in this reaction, you can see there is, come on. There's 2 moles of gas on the left and there's 2 moles of gas on the right. So although it's all gases, if you increase or decrease the pressure here, it won't have any effect. Because the reaction can't benefit by going left or right. So pressure will actually have no effect, even though it's all gas reaction. It tells you here the value of delta H always refers to the forward reaction. So the forward reaction is exothermic. And then, yeah, this is a silly point, not a silly point I'm making here. You see this delta H value, you won't really need this year. This delta H value is 13 kilojoules per mole. But because this reaction makes 2 moles of product, the actual amount of energy involved in this reaction is 26 kilojoules. But that's not a major point. It's not hugely important at this point. Now, equilibrium constant. Equilibrium constant is too big a topic to start now. I'll start that next lesson when everybody's here, and we haven't got time. It's a couple of minutes. All right, we're going to leave it there.